Hey, how's everybody doing? Welcome back to the Math for Healthcare video lecture series. And one thing we look at with probability distributions of random variables, one main thing, one of the big things, is called expected value. Now, well, of course, go in and define these things, but the expected value is kind of like it's not kind of like it is a long-term average. So you could think about it similar as taking the average of things, except for in probability. Just like when we say the probability of something is say zero point 0.2, what does that mean? It doesn't mean that it's going to happen one out of every 5 times in the long run, right? In the long run, after millions of trials, as it's going to, the proportion will even out to about 1/5 or 0.2. So similarly, the expected value is this long-term average. You do something, you write down what you got. You do something again, you write down what you got. For instance, let's say I was tossing 3 coins and I want to know the average number of heads. Well, what the expected value represent, we'll learn how to calculate it soon enough, but what is it calculating? It's saying if I were to do that over and over and over again, toss 3 coins and write down how many heads I got each time, after about a million plus times or whatever, I took the average of all that, I'd end up with the expected value. So it's the long term average. Okay, so remember that we defined the probability of a random variable in the last lecture, right? And it looks something like this. This is a chart here, right? And it just tells us the probability for each value in the range of a random variable x. And we'll turn back to our example where we're tossing 3 coins, all right? Here, and there's our probability distribution. Now, how do we find the long-term average or the expected value? Right? Turns out that it is basically just what we call a weighted average. You have 0 happens 1/8 of the time, so 0 times 1/8, plus 1 happens 3/8 of a time, plus 2 happens 3/8 of the time, and 3 happens 1/8 of the time. Turns out this ends up being, looks like 3/2, which is 1.5. The expected, well, x is the number of heads, so there are units on that. That is 1.5 heads when tossing 3 coins. And they're fair coins. We're assuming 1/2. All right, so now you may ask yourself, well, wait a second. We can't get 1.5 heads, and you're right. However, remember, whenever you take averages, you can get things that you can't get. For instance, if I only gave grades of 85, 90, 95, say, right? When I average those things together, I could get 92.3, and that's okay. So here, when we say expected number or the expected amount or the expected value, it's okay if it's not one of the values of x. Now, certainly it's got to be within the range of x, right? In this case, greater than or equal to 0 and less than or equal to 3. However, it doesn't have to be one of those integers, all right? And here we would say our expected value is 1.5 heads when tossing 3 coins. And notice there's units involved. They're units, whatever the units are, of my random variable. In this case, it was heads when tossing 3 coins. Okay, so what's our definition here? For a general formula, for the expected value of a random variable, x, right? We do, just like I said, it's going to be x1 times the probability 1. In my case, that probability 1 was the 1/8, right? The value times the probability of that value happening. So sometimes on a chart, I think of it as we do this times the probability, the value times the probability, plus the value times the probability, plus the value times the probability. Right? That's all this formula is giving us, and we just didn't want to put it out. I mean, you could rewrite it as x1 times the probability of x equal to x1 plus x2 times the probability x equals x2, x equals x2, and so on. This is our definition of random variable, and it gives us a measure of the long-term average, what we expect to get in the long-term average, right? And again, it doesn't have to be one of the integer values of x or one of the values of x. Now, I want to notice here is, so here we said, we already calculated this expected value of x equals 1.5, and heads when tossing 3 coins. Now, it's not too surprising that it's half, considering the probability of success is half, all right? And it turns out that, notice where's 3 halves or 1.5? Oh, it's right there. And so it is right in the center of that distribution, right there. Now, is it always going to be exactly in the center? No, this has to do with the distribution or the probability of success. In this case, the shape of the distribution. This distribution is symmetric around that middle line, or our expected value. And so that's why it looks that way. And again, we'd expect it because of the 1/2 probability. Right? When we look at it for, say, dice, it's going to be a little different. Right? Okay, so that's our expected value. But in general, even if it's not right in the center, it tries to find the center of the distribution. Okay? All right, let's see an example here. We got a package of 10 microwaves. There are 3 broken ones. A quality control engineer tests a random selection of 4 of these microwaves. We're going to let X be the random variable that is the number of broken microwaves in the quality control engineer's sample. Notice I'm defining my random variable there. Now, we want to find the expected number of broken microwaves in the sample. Okay. Well, we need the probability distribution before we find that expected value. All right. First of all, let's see here. What is the range of X going to be? Let's see here. We're pulling out. What can we have? We could have 0. We could have 1 bad one. We could have 2 broken ones. We could have 3 broken ones. And even though we're taking out a selection of 4, we only have 3 broken ones in there, so we can't have a fourth. So the range of X here is 0, 1, 2, and 3. All right, and here's our probability distribution in this case. And just as a reminder, you should be able to fill that out on your own. You could have stopped that and created this probability distribution on your own at this point. And we've called this a hypergeometric before. It's not binomial, it's hypergeometric. And let's see what happens here. So this is the probability of 0 bad ones in this first one, right? Probability of 0 bad ones. Probably X equals 0, same thing. And so there's 3 bad ones. We're choosing 0 times 7 good ones, and we're choosing 4 of those over 10 choose 4. And so on for the probability X is 1. That's going to be 3 choose 1 times 7 choose 3 divided by 10 choose 4. Remember with these, the 7 and 3 has to add to the 10. The 0, 4 has to add to the 4. The 1 and 3 has to add to the 4, so on and so forth. All right, so that's our probability distribution here. Now, we could see here, right? This is not going to be symmetric like the coins. We could visualize that real quick. Let's see. Let's put that in there. Put the table. We got what? 0, 1, 2, 3. And let's see. The probability of 0 was 1/6. The probability of 1 was 1/2. Let's see, the probability of 2 is 3/10. And the probability of 3 is 1/30. Okay, we'll zoom in onto that. And so there, notice it's a little bit further. There's a little bit more kind of heights, in a sense, on the left side. And then you have this, the probability of 3 being much less than the probability of 0. And similarly, the probability of 2 being much less than the probability of 1. So, you can imagine those dots being connected. And if I wanted to draw a little approximate, you could always draw like this. Right? Okay. So that's how we could visualize it. Sorry. I don't like that drawing. Good thing you didn't see it because my screen's not there. Alright, so what does that look like? That distribution, I mean, we could, it's a little roundabout, right? But we get, let's see, 1/6, we get 1/2, and we get 3/10. And then 1/30. So something like that, it looks like, yeah? That's what our distribution looks like. All right. And so not as symmetric as we saw with the last one. All right. And we got to find our expected value. So it's 0 times 1/6. Plus 1 times 1/2 plus 2 times 3/10 plus 3 times 1/30. I just wrote 3 times 1/30 as 3. All right. 3 times 1/30. Okay. And so I'm just going to quick calculate this. We end up with oh, I wrote something wrong there. Sorry. This is 3/10, not 3/15. I don't know why I wrote it that way. Okay, so that's going to be and we end up with 1.2. All right, so we get for our expected value here, it's going to be 1.2. And what are the units there? Broken microwaves. Okay. And that's, so let's see here. Where is that? That's, like I said, that's a little bit, instead of between this 1.5 here, it's over here. It's pretty close. I'll do it in a different color for you. It looks like somewhere around here is our expected value. All right. Ish. Good. Okay. Now, So that was a hypergeometric example, and starting with the probability distribution and finding our expected value. All right, let's see here. The game of roulette, as played in Las Vegas casinos, the wheel is divided into 38 compartments, numbered 1 through 36, 0, 00. One half of the numbers, 1 through 36, are red, the other half are black. And 0 and 00 are green. Of the many types of bet that are placed, one type involves betting on the outcome of the color of the winning number. For example, one may place a certain sum of money on black. If the winning number is black, one wins an amount equal to that bet placed, and the amount of the bet is returned. Otherwise, one loses the amount of the bet. Find the expected value of the winnings losses on a $20 bet placed on black. Okay, so first thing is define the random variable. We're going to let x be the dollars in winnings / losses on $20 bet on black. Okay. And so here the units are dollars. That's what we're going to have. All right, so let's see here. All right. So what's the range of x? Remember, that's what we got to start with. What's the range of x here? Well, certainly we could win $20, right? If it lands on black, that's what it's saying. We get the $20 bet placed on black, and we get the $20 back, and then we get a $20 extra, right, for payoff. So in our wallet, we have $20 more than we started with, right? Now, what about if it doesn't come up black? Then we have minus $20 less than we had before, right? So here, let's see. All right, so now we need the probability that I win $20, which is really the probability it comes up black. All right, and so let's see here. How many do we have? We have 18 are black, and there's how many total possibilities? 38, right? Because then we get the 0 and 00. 1 through 36 are black and red. And so that leaves what? 20 out of 38 is the probability of losing $20, or the probability that it's not black. All right? Now we got to find the expected value. All right? Hopefully, try to hit pause. Try and do this on your own. You got it. All right? This is going to be 20 times 18 over 38 plus, negative 20 times 20 over 38. No, I can't really. Let's see. I can't really do that in my head. Oh, am I? Yeah, 30. Good. Looks like it comes at expected value. I'm going to round it to 1.05. All right. And remember, that's dollars. So, on average, we're expected to lose $1.05 each time we place this bet. All right. And here, it's something to note is that casinos, the expected value has to be negative for the player, right? It's positive for the casino, negative for the player. They run on these sorts of things. They know it's going to come up. And remember what we said earlier with probabilities is this idea is Casinos is different than you, the better. Why? Because they're guaranteed, or they should be getting millions of customers, right? Whereas you could only bet your own thing. So they're guaranteed to find this long run average. Insurance companies do it similarly. They have this guarantee to find this long run average, whereas we as people, we don't. We can only use it as a pointer which way to go. All right? But, yep, here we're going to lose $1.05 in general. Okay, one nice thing about expectation is it's linear, meaning that for two random variables x and y, the expected value of x plus y equals the expected value of x plus the expected value of y. All right, and for a real number alpha, the expected number of alpha x equals, misprint, that's alpha times the expected value of x. My apologies. All right. Now, suppose a bookstore owner, let's see how we could use this. Suppose a bookstore owner gathers evidence that 25% of customers spend $20, 50% spend $10, and 20% spend $0. Find the expected amount a customer will spend in the store. All right, so we need our random variable. In this case, you could go ahead and try this on your own. In this case, we're going to be what? Dollars customer spends. Okay. And so we now have our probability distribution that we got to come up. What's the range of x? Well, looks like it's going to be either 0, 10, or 20. Probability that the customer spends $0 is 20%. Probability that they spend $10 is going to be 50%. And $20, oh boy. Let's change this so we make it a nice, this is 25%. I apologize, that was a typo there. So this is 25% and 25% there for the 20. And you could imagine, you could guess what's going to happen. And here we can see those probabilities. This is a symmetric, right? They're the same on each side and in the middle space. And so what should it be is we're guessing that the expected value is $10. But let's do the math. Why did I plug that in? I wasn't thinking straight. 10. Okay, of course, that comes out like we were thinking. And that's $10. That's $10 that they're going to spend. And that's in the long run. Now, how much revenue would the shop owner expect to make if there are 40 customers in a day? Remember, again, this is times the expected value of x. Well, what is that going to be? If x is one customer, then let's say y equals dollars spent by 40 customers. And so y equals 40x, right? It's just 40 of the x's. That's the same thing. And so now we use this rule here, and we get the expected value of y, or how much spent by 40 customers, and that's going to be the expected value of 40x, which equals 40 times the expected value of x. And so here looks like we know the expected value. That's just like we did last time. That's going to be $10. dollars. So this is equal to $400 spent by 40 customers. Okay. Good. All right. Hopefully that makes sense. All right. Now let's see here. Chuck Norris. He's considering two business ventures. One's a heli ski outfitter in Haines, and the other is Seattle startup. Chuck invests in the Seattle startup venture. There's a 30% chance his anticipated returns would be a loss of $20,000. 40% anticipated returns would be $40,000, and 30% his anticipated returns would be $80,000. All right. However, for the heli ski adventure, we have 20% chance that would loss of $5,000, 50% chance that would be a loss of $25,000, and 30% chance his returns would be $40,000. All right. So, what do we want to do here? We want to know which one should he do. All right. And classically, one of the things we do is look at the expected value to decide on that. Now, like I said, this is different than a casino where you're doing it over and over and over and over again with lots of customers, and you're going to come out to this expected value. Here, he's got one shot at it, but it's still a good pointer in the direction we should go. All right, so let's let X equals thousands of dollars return from the Seattle adventure or startup, and we'll let Y equal the thousands of dollars in return for the heli ski. All right, and so let's see here. We need two probability distributions, one for X, the Seattle, and one for Y, which is the heli ski. All right. Okay, so what could, we gotta look at a problem. What can the X random variable take on? What values can that take on? All right. Well, let's see here. We got a loss of $20,000, and that was 30%. And I'm just going to write minus 20 because I have my units in the thousands of dollars. All right. And that's, what's that, a 30% chance? We got a 40% chance, $40,000. 30% chance, oh, that looks pretty good, $80,000. Okay. Oh, no. No. How about the heli ski? 20% chance. Oops. 20% chance that you lose $5,000. And let's see here. What do we got next? 50% chance gaining $25,000. And a 30% chance of gaining $40,000. All right. Now, we want to find these expected values. All right. At this point, you should be able to do that on your own. Go ahead and hit pause and try and find those. But it's negative 20 times 0.3 plus 40 times 0.4 plus 80 times 0.3 let's see here. $46. And remember, that's in thousands of dollars. And now for the expected value of Y, I'm not going to write it all out. I'm just going to calculate it. Hopefully I do it right. You should write it all out. Expected value of Y comes out to be $23.5 thousand or $23,500. All right. So at first look is, well, as far as expected value, that's pointing towards a higher expected value. So on average, if you did this a number of times, you'd end up with a higher value from the Seattle startup. Now, let's think about this. What are some other things we want to think about? Well, one thing might be is that notice the Seattle, you have a 30% chance of losing $20,000. All right, some people may say that's too risky. 30% is pretty high. Three out of 10 times. You lose 20 grand. That's not that small of an amount. And whereas the heli-ski, you only have a 20% chance, and you'd only lose $5,000. All right, so it does seem, the Seattle's a little riskier, whereas, but can bring you more money, and usually you got to find the medium between those sorts of things. Okay. But certainly things to think about. Like I said, expected values, when it comes to where it's a single shot at it, you could use it to point the direction, but it doesn't mean you automatically do that. It's different when you're an insurance company or a casino or something like that, something that's going to happen millions of times. All right. Now, what happens if he invests in both? Well, we could use, what would he be investing in both? We'd want to know what's the expected value of X plus Y, the X and Y that we defined before. So the Seattle startup plus the Y startup, if you had that, right, what's the expected value? We could use our formula from the other page. This equals the expected value of X plus the expected value of Y. And what do we get here? I got to remind myself, 46 and 23.5. So we get 46, 23.5. Oh, geez, what did I get there? 69.5 thousand dollars if he invested in both. And that is the beauty of our linearity. Okay. Let X denote the random variable that gives the sum of the faces that fall uppermost when a pair of dice is rolled. Find the expected values of X. We've already computed the probabilities associated with each sum. And they're given the following distribution, right? And remember, this is it's a symmetric one, right? Symmetric around 7. Oh, well, what's that saying? Our guess is probably the expected value is 7. So we do the calculations. This 2 times 136 plus 3 times 236. And that comes out to be, I guess I have it here, 7. And so we expect the dice on average to sum to 7. This is the long run. Again, this is the long run expected value. All right. How about a raffle that offers a prize of $1,000, 2 second prizes of $300 each, and 20 third prizes of $10 each? If 10,000 tickets are sold at 50 cents each, find the expected payback for a person buying one ticket. Is this a fair game? Well, we haven't talked about a fair game, but what do you think is a fair game? What's your guess? Think about that for a minute. Oh, fair game is when the expected value is 0. You're not expected to win anything. You're not expected to lose anything. All right? Obviously, casinos can't run their business on a fair game. Now, again, this is not saying that you shouldn't go gamble, but know that in the long run, you're going to lose. Right? All right, so raffle offers prize. What do we need? We need let's do our random variable. We're going to say let x equal the dollars return from one ticket. Okay. And we're going to ignore the 50 cents because whether you win or you lose that 50 cents. Okay, so no matter what, that we're going to just ignore that part of it. And so here, what are different values? You could win, certainly $0. And then you could win $10. You could win $300. And you could win $1,000. Now we need those probabilities. Okay, the probability that you don't win anything. All right, let's see here. What is that? It's tickets. We assume the tickets are equally likely each ticket. And so let's see here. 0. How many tickets are going to have 0? Let's see. There's 20 third prizes, 2 second prizes, and 1 first prize. That's what? 22, 23. So it's going to be 1,000 minus 23. You could do that as a calculator if you want. I'm just going to write down that way. All over 1,000. Okay. Yeah, I guess I'll do it. That's what? It's going to be 977. Okay, and then the $10 was the 23rd prizes. So what's the probability of that happening? That's 20 over... this is 10,000 down here, right? 10,000 tickets. And so that means my math up here, that's 9,977 loser tickets. Okay? There's 20 third prize tickets, and that's out of 10,000. Okay? And then there are, let's see, how many? 2 $300 prizes. And lastly, there was $1,000. That's going to be 1 out of 10,000 wins $1,000. All right. And so we write our formula out. You should write that all down. I don't want to take up too much time. You could do that on your own. I'm just going to go ahead and calculate this. Notice we could do 0 times the 999.77. So we don't really have to worry about that term. And then the rest, I'm going to do in parentheses and then divide them all by 10,000 at the same time. All right, so we get 10 times 20 shift plus 300 times 2 plus 1,000 all divided by 10. Okay. So notice here we get the expected value of x is equal to 0.18, and that's in dollars. Now, notice it's not zero, so it's not a fair game, but really that was the return from one ticket. We weren't thinking about how much, we weren't thinking about the 50 cents. And really, you would say that a person expects to lose, because everyone has to buy that ticket, minus 50 cents, and we get negative 32 cents. And so, no, it's not a fair game. Okay. So, we'll continue with the binomial experiment next time. We're going to do one on binomial probability distributions next. Okay. All right. Thanks. See you next video.